Good morning, class. I sure do miss being able to be with you. I am getting better. I'm hoping that next week the doctor will clear me and allow me to be back. This week I still don't quite have the strength, and she's concerned about my immune system, so I do miss y'all. I'd rather be with you in person. I'm going to go ahead. I know that you've already prayed because my daughter's there leading class, so I'm going to go ahead and go back and review some of what Ryan taught you as far as the logic and the proofs. I will make sure that you don't have a test until we have met and you're able to ask any questions. And so we're going to do a lot of review today, and then I'll probably introduce one new concept at least. You should have your new notebooks, or at least the first few pages of your new notebook. Know that when I test you, the test will just be on logic and proofs. And again, I won't give that until I've met with you and know that you're ready. So let's go ahead and review all the definitions on logic. I do want you to write all of these definitions 4 times each for me and be ready to turn those in next week. There will be a quiz on logic. I know that Ryan, I believe, gave you a quiz, but I'm going to go ahead and give you the quiz on this and not count the one that he gave you. So I feel like it's important for us to have been able to go over all this before you have a quiz, but there will be a quiz next week on all of the vocabulary, and I will take up your work that you've written 4 times each. So make sure that you do that. When you write it, it'll help you learn, and also it's a real easy homework A to just turn in vocabulary. Remember, I do want it handwritten. I don't want it typed where you can copy and paste, so I do want your definitions handwritten for me. And so let's go over what all these definitions are. First, we're going to start with deductive reasoning. And deductive reasoning is to conclude something based on facts, definitions, or axioms. Okay, basically, an example might be if you see muddy shoe prints on the carpet, you conclude that somebody walked in the house with muddy shoes. Okay, that's a fact. In order for those footprints to be there, somebody had to put them there, so it's a fact. Another one might be, and the one in the book they use is, your brother has chocolate sauce all over his face, and you conclude that he ate chocolate sauce because it's on his face. So that would be based on a fact as well. The difference between deductive and inductive is inductive means it's kind of like what we do in science class. We do experiments over and over and over to prove that something is true. So this would be based on specific examples. So like the example gives in the book, you kick your cat and every time you do it scratches you. You conclude that if you kick your cat, you will get scratched. Okay? So you might, another one might be you put a pan of water on the stove and turn it on high and the water boils. You conclude that if you put water on the stove on high and leave it, that the water will boil. That's based on actual experiments that you do, something that you do. So almost like deductive is almost like something that you observe, and it's based on things that you see. Inductive would be something that it's happened to you over and over again. So it's actually an experience. So that might help you get that straight. So on number 1, you should have already done this in your book, but you're going to either identify as A, inductive, or B is deductive. You take 3 things and add them to 5 more things and count that you have 8 things. You repeat this several times and conclude that 3 plus 5 is 8. One of the hints in there is it says that you do it over again. You repeat it. So when you repeat something and it's an action, you're going to go with inductive reasoning. So that would be A. Okay? Moving along to the next definition, so you have deductive and inductive. The next one would be conditional statements. Conditional statements express a cause and effect relationship in the form of if P, then Q. An example of a cause and effect relationship would be like this. When you do your homework, or if you do your homework, then your grades will get better. So P would be when you do your homework, and Q would be your grades will get better. Here's a few more examples of that. If Amy goes to the store, then I gotta skip back. Whenever Amy goes to the store, she buys milk. So you would write that in. You have to have an if and a then in a conditional statement. So the regular sentence was whenever Amy goes to the store, she buys milk. So you would say, if Amy goes to the store, then she buys milk. Another one example in the book that gives you, angles are complementary because they add up to 180 degrees. You would say, if two angles add up to 180 degrees, then they are supplementary. So there's a couple examples for you. The next definitions that you want to do are hypothesis and conclusion. Now, if you've in my chemistry class, I do not want you to put that hypothesis an educated guess. That's true in science, that a hypothesis is an educated guess or prediction. But in geometry, it's the part of the conditional statement that follows the if. Like, if Amy goes to the store. Amy goes to the store is the hypothesis. Then the conclusion would be the second part. It would be after the then. So it would be, if Amy goes to the store, Amy goes to the store would be the hypothesis. Then she buys milk. She buys milk would be conclusion. Do not include the if in the hypothesis. Do not include the then in the conclusion. Whatever follows if is the hypothesis. Whatever follows then is the conclusion. So let's go ahead and look at some examples here. Now, I know these books that sometimes there are exceptions, but just accepting these as true, okay? If an animal is a dog, then it has a tail. So an animal is a dog is the hypothesis. It has a tail is conclusion. If a quadrilateral is regular, then it is a square. A quadrilateral is regular is hypothesis. Is a square is your conclusion. So number 1, every time you practice, you gain more skill. They want you to write the statement, the conditional statement. Remember, conditional statement is going to include an if and a then. So here's the sentence again. Every time you practice, you gain more skill. So your answer would be, if you practice, then you will gain more skill. You practice would be the hypothesis. You will gain more skill will be the conclusion. Moving right along to the law of detachment and the law of syllogism. So I'm going to go ahead and start here, read the notation at the top. This is on page 181. Sometimes it's easier to write some of these things with a kind of shorthand. So this is what the law of syllogism and law of detachment allows us to do. So here it goes. P stands for the statement, which I said is usually the hypothesis. Q stands for the second statement, which is usually a conclusion. R and S and so on can be additional statements. So if P, if a hypothesis, then Q can be written as P, and it does a little, it almost looks like an arrow. Draw this here. Okay? So we have P, Q. So what that means is, if P, then Q can be written as P, Q. When you see this, this actually means P implies. This means implies Q. So keep that in mind. That little arrow means implies Q. But it is the same as if P, then Q. So instead of having to write if P, then Q, you can just write P implies Q. That's kind of doing a shorthand, okay? Here's an example. P, the iPod is on. Q, it can play a song. Write P implies Q. You would write if the iPod is on, then it can play a song. Law of detachment. If you have a conditional statement where P implies Q, and the statement is true, then if P is true, then Q is true. Okay, so that's your definition. So let's say that if it is a car, it has a steering wheel is true. Well, your P is, your hypothesis is, if it is a car. If this is true, then your Q, it has to have a steering wheel, is also true. Here are some examples. If an animal is a dog, then it has a tail. Dougie is a dog. What can you conclude about Dougie? You can conclude that he has a tail. If an angle is obtuse, then it measures between 90 degrees and 180. Angle ABC is obtuse. What can you conclude about angle ABC? You can conclude that 90 degrees is less than the measure of angle ABC is less than 180 degrees. So that's your law of detachment. Law of syllogism. If you have two statements, P implies Q, and then Q implies R, and they are both true, then P implies R is also true. Here is how it goes. If I do my homework, then I will get better grades. If I get better grades, then my parents will be happy. Notice that the law of syllogism is much more detailed than the law of detachment. It gives you a little bit more information. So by the law of syllogism, If I do my homework, then my parents will be happy. Cool, huh? Here's another example. If the car has gas, then you can start it. If you can start the car, then you can drive to the store. So the car has gas. What can you conclude about the car? You can conclude that you can drive to the store. On the bottom, there's a note down there. I want you to pay attention to it. Sometimes a logic problem will say something like, assume the statement is true. What this means is that the statement could sometimes be false, but just pretend it's true for now. For example, like the dog having a tail, not all dogs have tails. Another example would be, if it is cloudy, then it is raining is true. Actually, sometimes it can be cloudy and there not be rain. So it isn't always true. So anytime that you see, you're going to pretend that it is a true statement. Okay? So number 1 on page 182, you're going to bubble A if it's the law of detachment, B if it's the law of syllogism. Remember, law of syllogism is going to be a little bit more detailed. Number 1, if you used to be a doctor, then you lost your patients. Sally used to be a doctor. What can you conclude? You can conclude that she lost her patients. Number 1 would be the law of detachment. It's just pretty specific. It's not giving more examples. So let's look at number 2. Well, let's not do number 2. Let's do number 5. Well, I want to find one that's a little bit easier to understand. Let's do 6. If John reads a book, then Tom watches TV. If Tom watches TV, then Joe eats ice cream. See, there's several things going on there. And so I'm going to go ahead and assume that that's going to be a law of syllogism. But it says John reads a book, and what can you conclude? You can conclude that Joe eats ice cream. Okay? Going on to a counterexample, being the next definition up there. Have you ever been in a situation where you were arguing with someone about something and you knew that they were wrong, but you weren't exactly sure how to point it out to them so that they would stop arguing? I've known people like that. They keep arguing. Well, here is a great way. It's called a counterexample. A counterexample is a specific example that proves that some statement is false. But specifically to logic, it is an example that is true for the hypothesis, P, and shows the conclusion, Q, is false. Here's what I'm talking about. Let's say someone says something stupid like, if an animal is a dog, it is a Labrador. A good counterexample might be a poodle. So what they're saying here is you can say that just because an animal is a dog doesn't mean that it's a Labrador, but instead of arguing that back and forth, you can give an example, a specific example of another type of dog that is not a Labrador. See how a poodle is a dog? It is true for P that an animal is a dog, but shows that it is possible to have a hypothesis to be true but it not be a Labrador. A bad counterexample would be a cat, because a cat is not a dog, okay? Let's see here. Here's another one. If an angle is acute, then it measures 35 degrees. Well, 35-degree angle is an acute angle, but there's a lot of other angles that would be acute. So you would give a specific example of another acute angle, 45 degrees, anything that's under 90 degrees. Okay? Here's some more examples to kind of look at. If a figure is a triangle, then it is isosceles. Well, there's several types of triangles that are not isosceles. You could do an equilateral, you could do a scalene. So there would be a couple other examples of triangles that would not be isosceles. Example 2, if you are a girl, then you are a blonde. So in this one, you would not just say a brunette or redhead. You would go ahead and give a specific example of someone that is a girl that is not blonde. So in the book it says Anne Hathaway, but it could be somebody that you know, but it has to be specific, okay? Example 3, if you are at school, then you are a teacher. Well, there's a lot of people that are at school that are not teachers. You have the principal, you have the students, you have the fly on the wall. Anyway, you want to give a specific example of something at school that is not a teacher, okay? I think that's enough examples to go over. But we want to bubble a letter of a counterexample for each on page 184. So number 1, if a figure is a polygon, then it is a triangle. So you want to give an example of a polygon that is not a triangle. Well, first of all, A is a circle. Circle is not a polygon. Remember, a polygon is made up of different sides, okay? B, an obtuse triangle, well, that is a triangle. C, an isosceles triangle, it's also a triangle. And D is a square. A square would be your answer. That is the only figure that is a polygon that is not a triangle, and it's specific, okay? On 185, you have to give specific examples yourself. It says, if an angle is acute, then it measures less than 80 degrees. So you would give an example that of an angle that is acute, that is less than 80. It can be anything, well, it has to be between 80 and 90, because let's go back and read it. If an angle is acute, then it measures less than 80 degrees. There are acute angles that are more than 80 degrees, 81, 82, 83, 84, 85, 86, 87, 88, and 89. So any of those answers would work. If an animal is a bird, then it can fly. Well, you need to think of a bird that can't fly. So a penguin would be a bird that doesn't fly. You would want to go ahead and give examples of that, specific examples. The next one would be conditional forms, and we're going to be talking about the conditional forms are converse, inverse, negation, and contrapositive. So let's mix it up a little bit. If you take a conditional statement and mix the order up, say flip it so that Q, if Q then P, instead of if P then Q, then you get a conditional form. Let's look at each of one of the conditional statements. If you used to be a doctor, then you lost your patients. For this statement, P, the hypothesis, you used to be a doctor, and Q, the conclusion, you lost your patients. The first one is called the converse. It means if Q, then P. So the converse of that statement would be to flip it. Instead of saying, if you used to be a doctor, then you lost your patients, the converse, these are not the shoes. The converse would be to flip the order. It would be if you lost your patients, then you used to be a doctor. The next one is called the inverse. The inverse is if not P, then not Q. And that's called a negation. When you have not or the symbol like that, that's called negation. And it's anytime you put a not in there, okay? Like make it negative or the opposite. To do this, add the word not or any contradiction with not, like isn't, wasn't, won't, etc. So here is the inverse of our statement. Remember, the original statement was, if you used to be a doctor, then you lost your patients. We're going to go ahead and leave it in the same order for the inverse, but we're going to put a not in there. If, or didn't, or a negative. If you didn't used to be a doctor, then you didn't lose your patients. So let's think a minute. The converse, we flipped the order. If you lost your patients, then you used to be a doctor. We had flipped it. Inverse, we go back to the original order and we just put a negation in there. If you didn't used to be a doctor, then you didn't lose your patients. The last one is called the contrapositive. It is the negation of the converse. Remember the converse, we flipped the order of the original statement, and then we're going to put negative, a negation in there. So if not Q, then not P. Also written as not Q implies not P. This one is very special and will help you answer a lot of really hard questions very quickly and easy. Check out the example. We want to write the converse, the inverse, and the contrapositive of each statement, and decide if each is true. So here's the first one. If an animal is a goose, then it has a beak. The converse would be to flip the order. If an animal has a beak, then it is a goose. Is that true? Well, actually it's false, because there's other things that have, that have beaks. So you'd want to give a counterexample, and that would be a robin has a beak. You want to provide that if it's false. The inverse would be the original order of the first statement, but putting a negation in there. If an animal is not a goose, then it does not have a beak. False, again, a robin has a beak. Contrapositive, we're going to go in the same order of the converse. If an animal does not have a beak, then it is not a goose. That is true, because geese do have beaks. Okay? Another example. If a triangle is a quadrilateral, then it has 3 equal sides. The converse, remember, is flipping the order. If a triangle has 3 equal sides, then it is equilateral. That's true. The inverse, if a triangle is not equilateral, then it does not have 3 equal sides. That is true. And the contrapositive is the same order as the converse with a negation in it. If a triangle does not have 3 equal sides, then it is not equilateral. And that's true. Notice it's really important to pay attention. If the original statement is true, then the converse is sometimes true, but not always. If it is, it's called a biconditional statement, meaning biconditional statements is true both ways. The inverse is sometimes true, but not always, and the contrapositive is always true. Soon you will see very complicated problems that will be easy to solve if you know that helpful fact. Okay, so let's look at number 1. If a figure is a square, then it is a rhombus. We're going to write the converse. Remember, the converse is going to flip the order. If a figure is a rhombus, then it is a square. The inverse of that would be the regular order, the original order, with a negation in it. If a figure is not a square, then it is not a rhombus. The contrapositive will be the order of the converse. In other words, flip from the original statement with a negation. If a figure is not a rhombus, then it is not a square. Let's look at number 2. If it is 6 o'clock, then we put on our tuxedos. The converse would be to flip the order. If we put on our tuxedos, then it is 6 o'clock. The inverse, go back to the original statement and negate it. If it is not 6 o'clock, then we don't put on our tuxedos. And the contrapositive is, if we don't put on our tuxedos, then it is not 6 o'clock, the same order as the converse. Okay, so you've probably already done these, but I want you to go ahead and make sure that you have. You come to biconditional statements on 191. These go both ways. A biconditional statement is a statement that is true both forward and backwards. Okay, that means that the original statement and its converse are both true. Here's some examples. If a figure is a triangle, then it has 3 sides. That is true. The converse is to flip the order. If a figure has 3 sides, then it is a triangle. That is also true. Statement. If 2 lines are perpendicular, then they intersect at right angles. That's true. The converse, you flip it around. If 2 lines intersect at right angles, they are perpendicular. That is also true. Notice that all of these, both the statement and its converse, are true. These are also commonly referred to as definitions. They are very useful because if you want to know if 2 lines intersect at right angles, for example, all you have to show or know is that they are perpendicular. Conversely, if you know that they are perpendicular, all you have to do is find out if they intersect at right angles. This will come in handy when you do proofs. All right, so let's go ahead and look at these. So how do you tell if a statement is a biconditional statement? All you have to do is write its converse, and if the converse is true as well, then the statement is biconditional. Look at this. Decide if each statement is biconditional statement. If it's not, you got to give a counterexample for the converse. Statement. If 2 lines are parallel, then they never intersect. The converse would be, if 2 lines in a plane never intersect, then they are parallel. That's true, so the statement is biconditional. Statement. If an angle measures 28 degrees, then it is acute. That statement is true. But if you flip it, if an angle is acute, then it measures 28 degrees. Well, there's other angles that are acute. So you would say false and give another example. Example in the book is 38 degrees, but any other acute angle. So that would not be a biconditional statement. Biconditional statements are often written as IFF. That means if and only if. A, then B. Okay? So IFF means if and only if, and identifies the statement as biconditional. Also, the notation of A, you have an arrow going both ways because A implies B or B can imply A is used, means that A implies B and B implies A, meaning they're both true, they're true both ways. Write if 2 lines are parallel, then they never intersect as a biconditional statement. You would write IFF, that means if and only if, shorthand for that. 2 lines are parallel, then they never intersect. Okay? So you'll want to go ahead and make sure that you've completed through 192. I'm getting a little tired and a little bit short-winded, so I'm going to go ahead and stop there. I know that you have done most of this work. I'm going to go ahead, instead of giving you a new concept, I'm going to go ahead and come up with some things for you to be able to review. There may be some proofs on there for you to try, so if you were a little bit confused on the proofs, you can skip that part and we'll do them in class together next week. I do want to make sure that I'm there to go over proofs with you, even though you had a sub, because some of you might have really got it and you feel comfortable, but others of you may feel a little bit iffy about it. So I want to make sure that I'm there to make sure you understand. So let's make sure that you have completed through 192 in your book. I will look at that next week to make sure that you have done that. I do want you to turn in your vocabulary that you've written 4 times each, and I will send my daughter with some things for you to practice some more of this logic stuff, some handouts. And won't be a lot of homework this week. We really, in geometry this year, we're really ahead of where we've been in the past. So I'm not too concerned about us having missed class last week. We should be perfectly fine. It's more important that we slow down with me not being there and make sure that you understand everything than it is to continue to rush through. Rushing through, we could add more things and you would have more homework, but I think it's important to kind of pull back. This coronavirus has been rough. It's been an unusual time, so we're going to pull back and make sure you understand everything as we go forward. So anyhow, if you have any questions, please email me or give me a call, and I hope that you have a wonderful week. Hopefully, I'll be back in class next week. Take care. Bye-bye.